not this Friday, that is next. Alright, so welcome to the next lecture on signals and systems, and we proceed today by looking again at the linear shift invariant system in much more detail. In the previous lecture, recall that we have studied the effect of cascading indirectly in a linear shift invariant system. In other words, we looked at the properties of convolution. We saw that convolution was commutative. That means that the order of the two sequences, the order of the two signals that were convolved was irrelevant, right? It didn't matter whether you convolved x with h or h with x, right? The result was the same. We also showed in the previous lecture that convolution is associative. That means, so let's summarize them. Convolution is commutative. That means x convolved with h is the same as h convolved with x. I must of course emphasize that x and h are both signals here. Associative. Namely, x convolved with h convolved with g is the same as x convolved with h and then convolved with g. We bring up now a third property of convolution, namely its property of distribution over addition. Now, what do we mean by distribution? Distribution means that the convolution of a linear combination is the corresponding linear combination of the convolutions, right? So, for example, x convolved with alpha h1 plus beta h2 is equal to alpha times x convolved with h1 plus beta times x convolved with h2. Here alpha and beta are arbitrary constants over the field on which the signals are defined. So if I am talking about a complex signal, these could be complex. In general, we talk about signals that are complex. I mean, that's the most general situation that we deal with. So in general, alpha and beta can be complex numbers. In a specific, of course, needless to say, once it holds for complex numbers, it also holds for real numbers, it also holds for integers and so on. Right? So the most general possibility here is that alpha and beta are complex numbers. Now, I don't think it is very difficult to prove this. All that one needs to do is to write an expression for alpha. In fact, this is not surprising. You see, I don't even need to prove it really. This is in a way, the distributive property is a restatement of the property of linearity. Right? I mean, we are saying that, you see, look at it this way. I mean, see, don't think of h1 and h2 as impulse response. For the moment, think of x as an impulse response of an LSI system or an LTI system and h1 and h2 as inputs. Alright? In that case, you know that convolution is commutative. So this expression on the left hand side is equivalent to applying an input alpha times h1 plus beta times h2 to the LSI system with impulse response x. Alright? And because the system is LSI, the output obeys superposition. The output would be alpha times the output corresponding only to H1 plus beta times the output corresponding only to H2, and therefore the property of distributivity is in fact a consequence of linearity. But of course one can also prove it. You see, this is an interpretation, and I would call it an interpretation. One can also think of convolution as an operation and prove the same thing by expanding the integral, right? I don't think that's very difficult to do, so I shall not write down all the steps explicitly, but these properties are of great consequence. Let's recapitulate rather the implication of each of these properties. Commutativity. Now you see, actually we have interpreted the effect of commutativity after we have interpreted that of associativity. We said associativity tells us that if I have a cascade of two LSI systems with impulse response H and G respectively, then this is the output corresponding to that. But because of the property of associativity, it is clear that there is an equivalent LSI system with impulse response H convolved with G. Alright. Now we have used commutativity over and above that. So we have said because convolution is commutative, H convolved with G is equal to G convolved with H, and therefore it does not affect the output if we interchange the order of the systems in the cascade. Right. Now this can be carried further. The property of commutativity and associativity together can be carried recursively to show that if I have a cascade of LSI systems numbering more than 2, so if I have a cascade of 3 LSI systems for example, right, then it still does not matter which order we place those LSI systems because of the joint properties of commutativity and associativity. Right. So I repeat, the consequence of commutativity and associativity is that no matter how many systems I put in a cascade, if all of them are linear and shift invariant, then the order of the systems in the cascade or in the series connection, so to speak, is not relevant. I must again emphasize this is true only for LSI systems, not for systems that are not LSI. We will soon take an example to show that if the system is not LSI, it does not obey this property at all. Right? Now what does the property of distributivity mean from an interpretation point of view? Distributivity refers to decomposition into parallel form. Just as you have a cascade or a series interconnection, one can have a parallel interconnection of systems. Right? So the idea is as follows. Let me draw the diagram to illustrate. If I have a parallel interconnection, I mean that I am giving the same input to two LSI systems with impulse. So now you see I use the shorthand notation. I will write a block with H1 and write LSI on top to mean I have an LSI system with impulse response H1. And here I have another LSI system with impulse response H2. I multiply the output of this by alpha and the output of this by beta, and add them. Now the distributive property tells me that the output of this system is the same as the output of the following system. So the distributive property says the output observed here and the output observed here are the same. So these are equivalent. We say two systems are equivalent if they have the same input output relationship. In fact, in systems, it is equivalence which is more relevant than there is no precise notion of equality in systems, right? I mean, we say two systems are equal if of course they have the same input output relationship, but they are also really constructed in the same way. Now, you know, it's normally not meaningful to talk about construction. For example, you know, are you talking about construction out of electrical elements, construction out of mechanical elements, construction out of hydraulic elements? So you see, you could have a situation where the input output relationships are the same, and from our point of view the systems are really the same, so we call them equivalent, even though they are not equal because they are not constructed in the same way. They might, one of them might be constructed out of mechanical and the other out of electrical elements. Yeah. So these are equivalent systems, right? They have the same input output relationship. Now this is what is called a parallel interconnection. So here we've generalized the notion of series interconnection and parallel interconnection in LSI systems, and we notice that both of them have an interpretation when we talk about the properties of convolution. All right. Now the next issue that we need to discuss, which is also very important, is to first show that, you know, this idea of interchanging the elements in a cascade is not true when the systems are not LSI. So let us take an example. Let's take a counter example to show that if we have two systems in cascade that are not linear and shift invariant, that is, if they disobey at least one of the properties, then the interchange cannot be permitted if we wish equivalence to be true, right? So let us consider the cascade of the following systems. The first system is S1 described by Yt is t times xt. And the second is a system that squares the input. So we have Yt is xt squared. Now we ask ourselves, will it be acceptable to interchange the order? First, let's reason out whether these systems are linear and shift invariant. Well, it's very clear that this system is not linear. It is shift invariant. It is shift invariant, right? On the other hand, this system is linear but not shift invariant, and we've cascaded them. Now, what is the output in this? So, if I have xt as the input here, what is the output here? Well, here clearly the output is t times xt, so I can clearly see the output here is going to be the square of that, namely t squared times x squared t. On the other hand, if I happen to interchange the order, right? So if I put S2 before S1, what would be the output? So at this point I would get the square of xt, and at this point I would get t times that result, so I would get t times x squared t, and these are not equal. And therefore an interchange of order is not permissible. All right. Now this is also true if one of the systems is linear and shift invariant. So even if I have a cascade of two systems, one of which is linear and shift invariant and the other is not, still it is not acceptable to interchange the order. we will take an example, and in taking that example, we shall bring up a new concept. We shall use a very special linear shift invariant system, the differentiator. So we will first show that the differentiator is an example of a linear shift invariant system. So lemma the differentiator is a linear shift invariant system. Now please note, this is not the same as the result that we proved earlier. Earlier we have shown that when you feed to an LSI system the derivative of a particular input xt, the result is the derivative of the corresponding output yt. So we have shown that if xt when fed to a linear shift invariant system results in the output yt, then the derivative of xt, x dash t so to speak, or dxt dt results in dyt dt. We have shown that earlier. But what I am proving here is not the same thing. That is why I am emphasizing it a little more carefully. I am showing that if I think of the differentiator as a system, that means if I have the following system S, where when you feed in xt, the output is yt given by dxt dt. Then this system is linear and shift invariant, right? Actually, it's not at all difficult to show, right? Linearity follows almost trivially. It follows from the linearity of differentiation. So it's very, very clear that if we feed in alpha x1t plus beta x2t to this system, what we will get is alpha dx1t dt plus beta dx2t dt which clearly shows the property of linearity. Alright, so linearity is not a problem at all. In fact, neither really is shift invariance. It can be shown by the chain rule, right? Can be shown by the chain rule. So in fact, let then the system be x of t minus t0, and let's call x of t minus t0 gt. When we feed this into the system, the output is dgt dt, alright, and dgt dt, as you can see, is clearly dx dt evaluated at t minus t0 and ddt of t minus t0. It's quite clear, alright, that's 1. So since this is 1, it need not be written. Alright, so therefore by the chain rule of differentiation, it's very clear that the differentiator also obeys shift invariance. Well, that can be seen even graphically. If I shift a signal forward or backward by a certain amount t0, the derivative also shifts forward or backward by the same amount t0. That's not difficult to see graphically also, right? So the differentiator is one very special example of a linear shift invariant system. And naturally we encounter a very important question here then. What is the impulse response of a differentiator? Right? That's a tricky question. We don't know at the moment. Well, technically the way we should find the impulse response is to feed to the differentiator an impulse, a unit impulse, and look at the output. But we don't know what happens when you differentiate an impulse. So let it remain a mystery for the moment, right? Let's let it remain a mystery for the moment. We'll take it up later, after a while. It would lead us to a whole new class of objects in mathematics, or in signals and systems. So we'll take that issue up later. But for the moment, we'll be satisfied with the observation that the differentiator is a linear shift invariant system. And therefore, we shall now look at a situation where we cascade the following systems. We cascade a system S1 and the differentiator. We'll denote the differentiator in short by ddt like this. The system S1 is described by yt is t times xt. This describes the system S1. Alright, so let's look at the output of this cascade. Well, at this point the output is t times xt, and therefore when you differentiate it, the output is going to be t times dxt dt by the rule of products plus xt times the derivative of t, which is 1. This is the output. Is that right? On the other hand, if I happen to interchange the order in the cascade, what do we get? We get the derivative of xt here. And if we happen to feed this to the system S1, the output then becomes just t times dxt dt. And these are not equal. Yeah? So it's very clear that even if one of the two systems in the cascade is not linear and shift invariant and the other is, still an interchange of the order is not acceptable. So this proves that it's not enough that one of them be LSI. Both need to be LSI. Now the next issue that we wish to address is as follows. For an LSI system, the impulse response is the whole and soul. Right? So if I know the impulse response to an LSI system, I know everything about the LSI system. Now that must be able to answer a few questions for me. In the beginning, when we discussed system properties, we talked about other system properties as well. Causality, stability, memory, right? Now, naturally, we ask ourselves, suppose an LSI system has one or more of these properties. What can we say about its impulse response? In other words, since the impulse response characterizes the LSI system completely, there must be something peculiar to the impulse response, say for example, of causal systems, which are LSI in addition, right? Or impulse response of stable LSI systems, or impulse response of LSI systems without memory or with memory. Yeah? So we should be able to look at the impulse response and come to a conclusion, or reason out from the impulse response entirely whether the system is causal, whether it is stable, and whether or not it has memory. Right? Please remember, the properties of causality, memory, and stability are independent of linearity and shift invariance. So as I emphasized right in the beginning, a system could have any of these properties and not be LSI, or it could be LSI. Right? But now we are looking at LSI systems that have or have not one of these properties. Let's begin with the property of memory. So you see, that's the simplest case to handle. all right. Well, all that we mean is, see, if an LSI system has memory, in fact, it's very easy to see. In an LSI system, if I know that the impulse response is ht, then yt is x lambda, or let's write it the other way. Let's write xt minus lambda h lambda this time. That will make it clear. Now clearly, if the LSI system has no memory, then yt must depend only on xt. So that means this integral should just pick out some multiple of xt. That's the only possibility here. Because after all, yt is a linear combination from this of many xt's, right? xt and many other xt minus lambdas. Now for a system without memory, if the LSI system does not have memory, then except for xt, no other, no other lambda, that is except for lambda equal to 0, no other lambda should get picked out. So what does it mean? It means the impulse response, what do you think it means? Like, let me ask the class. So what kind of an h lambda should we have so that this system lacks memory? Now, well, the hint is that it should simply, I am giving you a hint, it picks up, somehow this integral picks up the value lambda equal to 0, right? Yes, so, yeah, that's my. H lambda should be a multiple of the unit impulse, that's right. So the requirement is that the impulse response must just be a multiple of the unit impulse, right? So h lambda must be some constant, let's say k0 times delta lambda. Because now you can see that's the case, then it will simply pick up, the value at lambda equal to 0 and multiply it by k0. So in fact, now it also tells us, what is the most general with and without. So now here we are talking about systems without memory, right? So if an LSI system has no memory, then h lambda is a multiple of the unit impulse. All right? Naturally, if an LSI system has memory, then at least some other, there are some additional at least impulses or spread in h lambda. So in h lambda there is not simply a unit impulse, it is anything more than that, has memory, right? In fact, that also indicates what is the most general class of LSI systems without memory. In fact, they are trivial. LSI systems without memory are simply multiplication operations. Yeah. So what is an LSI system without memory? Without memory is just an amplifier, so to speak, or attenuator. I mean, you should interpret amplifier also as attenuator. It simply multiplies the input by a constant. So please note that LSI systems with memory are really very trivial systems. But systems that are not LSI but which don't have memory, right, are not trivial. They can do some non-trivial things. Okay. Now I must open a question here. What about the differentiator? Right? What can we say? Does it have memory? Yes, the differentiator has memory. That's because in a differentiator you're not really looking only at the current point. You're looking at a neighborhood. So that has memory. Right? So I must emphasize, though it, on the surface it may appear that, when I know the expression, suppose I know xt sine t, and I can find out the output yt is equal to d dt sine t, which is cos t at that point t. No, that's deceptive. Because in reasoning that cos t is the derivative of sine t, you looked at the neighborhood of the point t. Right? So therefore, a differentiator is an LSI system, but it has memory. But of course, it's still a mystery what the impulse response is. Alright, so memory was handled very easily. Now let's look at causality. Right? So there again we write down the relationship yt is integral. Here again we prefer to write h lambda instead of, so h lambda xt minus lambda d lambda now. You see, what does causality mean? Well, a formal definition of causality says that if I have two inputs x1 and x2, both of which are identical up to a point, say t equal to t0, the outputs must also be identical up to the point t equal to t0. That's how we define causality. Now with this expression, when can that happen? That can happen only if yt is not influenced by xt for t great, or by those xt minus lambda where lambda is negative. Well, in other words, you must not have, you see, the point is the influence on yt should not come from xt minus lambda, where xt minus lambda refer to future values of x. So if t is equal to 3, for example, I should not have an influence of x of 4 or x of 6 or x of 10 or even of x of 3.1, because the moment I have an influence of a future value of x, then it can affect my current output, even though you see, if I have two inputs x1 and x2, both of which are identical up to t0, but if my output is affected by future inputs, then it is possible that even though the two inputs are identical up to t0, the outputs could be different because they are influenced by the changes in the two inputs in the future. Right? So what is the reflection? What are we saying in terms of h lambda? I put the question again before the class. What is the condition on h of lambda? We have identified it qualitatively, right? What is the condition qualitatively? Qualitatively, yt must not be influenced by future values of x. So how do we express it quantitatively in terms of the h lambda? Yeah, anyone? Can I have a specific answer from someone? Yes, Manasa, yeah. That's right. So if the LSI system is causal, h lambda must be equal to 0 for all lambda less than 0. Yeah, as simple as that. We don't care what happens for lambda greater than or equal to 0, but for lambda less than 0, there must be a strict null. So causality also has been handled quite easily, right? Now we come to stability. That's not so simple to do. So we address the question of stability. Now, when would we say an LSI system is stable? Now, Similarly, we realize that stability or the absence of it relates to the fact that when you have a bounded input, the output is also bounded. So we need to look at a bounded input first. The moment you say you're looking at a bounded input, you're looking at magnitudes. So the first thing we need to do is to put a constraint on the magnitude of the output. So let's write down the expression for the output first again. Yt is integral. Well, here it would, it could be written either way. But let's write again h lambda as we've done before. H lambda x t minus lambda d lambda. And therefore, the modulus of yt is the modulus of this integral. Alright? But you see, if you think of the integral as a limit of many summations, then it is very clear that the modulus of a sum is less than equal to the sum of the moduli. So therefore, this integral is going to be less than equal. So I will continue on this side. This is going to be less than or equal to integral modulus of this, right? So that's modulus h lambda modulus x t minus lambda d lambda. Now I must use a word of caution here. We are talking about indefinite and infinite integrals here. You see, I am talking about an integral for lambda running all from minus infinity to plus infinity. In all such situations, we need to worry about convergence. When we have a finite integral, there is never a problem about convergence with functions, not with objects. There could be a problem with objects. I mean, with generalized functions. If there are impulses, you could have some trouble. But if there are functions, and if you are working on a finite interval, there is never really a serious problem about, writing down an integral. We may not be able to evaluate it in closed form, but we can certainly assume that it has a finite or a calculable value, and we can perhaps calculate it numerically. But when we have an infinite integral, we need to worry about convergence. So for example, this quantity may or may not converge. In other words, it may or may not tend towards a finite value, right? In any case, let us take the situation where xt is bounded. Okay, so let xt, so now what we are trying to do is establish the requirement for stability. So first we will establish a sufficient condition for stability. So how do we test stability? We test it by giving the system a bounded input, right? So let the input be bounded. By mx. That means mod xt minus lambda is less than equal to mx. Of course, it is greater than equal to 0 obviously, and this is strictly less than infinity. It's a finite constant, mx. Okay. Now what can we say about this integral then? If it does converge, it is certainly less than equal to integral mod h lambda d lambda multiplied by mx, because mx is independent of lambda. Is that right? So it's very clear that if this quantity happens to converge, that means if this quantity is finite, then we are guaranteed that the system is stable, because the output has a bound of mx times this. If this is a finite quantity, then the output is also bounded, right? So what is our conclusion? I think we should write it down clearly here. If this quantity is bounded, if this is finite, the output is bounded, and the system is stable. So what are we saying? It's a statement of sufficiency. It's a statement of sufficiency. It is sufficient that this be finite for the system to be stable. We are not making a statement of necessity here. That means it's not clear from this whether only a system which obeys this will be stable. In other words, can we conclude because the system is stable that this is finite? It's not clear from this argument. I must emphasize this because that's what we're going to do next. We're going to ask ourselves whether it is, we need, see, sufficiency means this might be more than what is required. So we have to ask ourselves, do we really require this much, or can we do with less? Now how do we answer such a question? We answer either by showing that there are stable systems which can do with less, or by showing that unless this is true, there is always this nasty input which will cause the system to demonstrate its instability. Alright, so we'll take the latter approach. Okay. So what do we need to do? Let's put down the problem that we are addressing. So this condition, the condition integral mod h lambda d lambda is finite, is sufficient for stability. Is it necessary? In other words, can I come out, as I said, with a nasty input, with a troublesome input, which can force the system to demonstrate its instability unless this is true? Okay, so we'll try and now define a nasty input which would force the system to demonstrate its instability in the absence of this condition. Yeah? How shall we do that? Let's look at the integral once again. So we have yt is integral. Now here again we have a choice. Alright, let's stick to that h lambda xt minus lambda. Now you see, I could construct this input by experience, but let's reason out what we want out of that input. You see, what are we trying to do? Try and understand. What are we trying to do? We are trying to look for an input x which will force that condition to come out. So which means somehow we have to force this h lambda to become modulus h lambda. And how can we force it to become modulus h lambda? By multiplying by the complex conjugate. You see, please remember, don't forget that H lambda in general is complex. Of course, it can be positive or negative even if it is real. So, notwithstanding the fact that it could be, even if it is real, it could still be positive or negative. In fact, let's keep it at complex to take care of the most general case. So, somewhere we need to multiply by a complex conjugate. But if we multiply by a complex conjugate here, then I would get the square of the modulus. So, I also need to divide by one modulus somewhere. Now, you see, the point is this: what are we trying? You must be very clear about what we are trying to do in this proof. You see, now we are showing necessity. So, what does it mean? It means that if you claim the system is stable, then I should be able to show this condition is true because here is a bounded input. So, we are going to produce, here is a bounded input, which when I apply to the system would cause that condition to emerge. That's what we are trying to do. So, I am trying to look for a bounded input which would force that condition to manifest itself. Alright? And please remember, here the choice of input is with us. See, when you say the system is, you are showing necessity, so the choice of input is with you. So, you can test it with any input that you wish which is bounded, and the output must be bounded. So, you can choose the most nasty input. Now, what is the most nasty input, as I said? Now you see, take any, it doesn't matter which t you take. Take any particular t. In fact, if you wish, take t equal to 0. Right? So, take t equal to 0. So, I have y of 0 is integral h lambda x of minus lambda d lambda. And here what I shall do is, I shall choose this very nasty input x of minus lambda is the following. It is 0 if h lambda is equal to 0. So, I am defining the input at every point, right? If at that point, please note, x of minus lambda is equal to 0 if h at lambda is 0. So, for example, x at minus 5 is 0 if h at 5 is 0, right? So, I look at the corresponding negative point in the impulse response and put it equal to 0 if that impulse response point is 0. If it is not 0, I do the following. I have h bar lambda divided by mod h lambda. If h lambda is not 0. Right? Now, why did I take care of this condition separately? Because of this problem. Here, since I am dividing by h lambda, I must not divide by 0. So, I took care of the h lambda equal to 0 separately. Now, what can I say about x of lambda? Is it bounded? In fact, what is the bound? Let me ask the class. What is the bound? Anyone? Yeah. Yeah? The bound is 1, is that right? What is the bound? How do you define the bound? Yeah, the maximum of modulus of x lambda. Clearly that's equal to 1. In fact, the modulus of x lambda is either 1 or 0. If h of minus lambda is 0, then in fact the x lambda corresponding to that is 0. And if it's not equal to 0, then it has a magnitude of 1. So x lambda either has a magnitude of 1 or has a magnitude of 0. Okay. Now substitute this input. So now let's apply this input to this LSI system. Now, well, in place of x lambda, that's very clear. You see, here I can see wherever h lambda is 0, anyway there's a 0 here. So it doesn't, this is 0, so it doesn't affect the integral. Wherever it is non-zero, I put along with it h bar lambda. Here bar of course denotes complex conjugate, divided by mod h lambda, d lambda. And what is this? This is integral mod h lambda squared by mod h lambda d lambda, integrate all lambda such that mod h lambda is not 0. Okay. And naturally, where h lambda is 0, anyway the initial integral was 0. So it doesn't affect the, right? So this is y of 0. Now what is this output? This is integral mod h lambda d lambda over all lambda such that mod h lambda is not equal to 0. But then, you see, wherever mod h lambda is 0, anyway there is no contribution, so I can write this down simply as integral mod h lambda d lambda. Is it right? Yes? Now, this is y0. And you claim the output is bounded, the input is bounded, so the system is stable, the output must be bounded. So in particular y0 must have a finite bound, so this must be bounded. Right? So if the system is stable, it is necessary that this be finite. Alright? So let's conclude. If the system is stable, then this, that is y of 0, must be bounded. That means integral mod h lambda d lambda is finite. Alright, and therefore it proves the necessity of the condition as well. It also, so we have now proved a very important theorem in the context of LSI systems. Let us state the theorem formally. An LSI system with impulse response Ht is stable if and only if Ht is absolutely integrable. That means integral mod Ht dt is finite. This condition is called condition of absolute integrability. Absolute integral means the integral of the absolute value. So here we integrate the absolute value of the impulse response. So it's called the absolute integral of the impulse response. So what are we saying? The absolute integral of the impulse response must converge, must be finite in order that the LSI system be stable. And this is both necessary and sufficient. We've just shown it. Yes? So we conclude the lecture here today and proceed to the next. We take up a slightly different, detour from what we've been discussing all this while. Just to recall what we did in the previous lecture, we had completed our discussion of the properties of LSI systems, but specifically continuous time.